There's something about rotation that nobody really thinks about. And I mean nobody. You've watched a figure skater pull her arms in and spin faster. You've seen the way water drains from a bathtub in a slow, lazy spiral. You've looked at pictures of galaxies, those gorgeous, sweeping pinwheels of light, and thought, yeah, beautiful. But here on Feynman's path, we want to go one layer deeper than that. Because here's the thing. You've never actually asked why. Why does everything spin? Not just planets, not just galaxies. Everything. The sun. Every storm system that's ever torn a coastline apart. The black holes at the centers of galaxies. The neutron stars flashing their radio beams across the cosmos. Even the drain in your bathtub. All of it. Spinning. Always. Spinning. Is that a coincidence? A quirk? Some odd preference the universe developed over 14 billion years? It is not. And once you understand why, the way you look at literally everything around you will shift. I'm not being dramatic when I say that. The law at the heart of this story is one of the most unbreakable laws in all of physics. And by the end of today, you're going to understand it not as a formula, not as a textbook definition, but as something you feel in your gut. Because here's the part that will knock you sideways. The reason everything spins is the same reason you exist. Full stop. Without rotation, there are no planets. Without planets, there's no Earth. Without Earth, there's no you, no me, no this conversation. The universe's tendency to spin is not a decoration. It is the mechanism by which a cold, featureless gas cloud became the world you're living in right now. Let's take this apart. Slowly. From the very beginning. Here's what most people assume. Planets orbit stars because gravity pulls them in. The Earth spins on its axis because, well, that's just how it formed. The universe is full of spinning things because space is mysterious and grand, and that's what space does. Most of us nod at that explanation and move on. But that explanation has a fatal flaw buried inside it. We are confusing the result for the cause. Gravity does not create rotation. It's almost the opposite. A tiny, nearly imperceptible wobble, something so small you wouldn't even notice it, that wobble is the seed. And gravity is what takes that seed and turns it into the most spectacular structures in the observable universe. Let me show you exactly how that works. Imagine a cloud of gas floating in empty space. Just gas. Hydrogen, mostly. Drifting. No planets yet. No stars. What happens to it? Well, think about rush hour on the subway. People standing on the platform, and slowly, gradually, they start drifting toward the center of the car. Not because anyone pushed them. Just because there are more people, there's more crowding, and bodies tend to move toward where there's room until eventually they're all pressed together in the middle. Gas particles do almost exactly the same thing. They feel each other's gravity, tiny as it is, and they start a slow, patient drift toward the center of the cloud. This is called gravitational collapse, and it's how every star in the history of the universe was born. Now here's the question that changes everything. Was that gas cloud perfectly still? Think about it before you answer. You're picturing a cloud in space, serene, motionless, like something in a painting. But nothing in the universe is ever perfectly still. Not a single thing. Maybe a nearby star exploded and sent a shockwave rippling through the gas. Maybe temperature differences in the cloud caused currents to flow, the way warm and cool air move against each other on a summer afternoon. Maybe the gravitational tug of some distant object gave the cloud a barely perceptible nudge. Whatever the cause, every part of that gas cloud was moving just slightly, just a little, just enough, each piece drifting in a slightly different direction than the others. Hold on to that. That tiny, random, almost nothing motion is the most important fact in this entire story. Now the cloud starts collapsing. Gravity is pulling everything inward. And as it does, what happens to all those little random motions? Some of them cancel out. A piece moving left collides with a piece moving right, and they knock each other's momentum flat. A piece moving up meets one moving down, and they neutralize. But here's the thing, and this is absolutely critical. Those cancellations are never perfect. In the real universe, with real physics, with countless particles all nudging each other in slightly different ways, there is always some net rotation left over. Always. There is no physical law, no mathematical possibility by which all of those random motions cancel out to exactly zero, so what's left is a tiny residual spin, barely there. If you were watching from outside, you might not even see it. It's like a mug of coffee on your desk, wobbling so slightly that you can't tell whether it moved at all, and then gravity does something astonishing. Have you ever watched a figure skater? She starts spinning slowly, arms out wide, and then she pulls her arms in. tight to her chest. And suddenly she's a blur. The speed is almost violent. She didn't push off the ice again. She didn't do anything except move her mass closer to the center of her rotation. That's not magic. That's angular momentum conservation. Here's the intuition behind it. A rotating object has what physicists call angular momentum, a kind of stubbornness about its spin. And that stubbornness doesn't just persist, it insists. The total angular momentum of a spinning system stays constant unless something from the outside interferes. So if the system gets smaller, if the mass moves closer to the center, the rotation has to speed up to compensate. It has no choice. The physics demands it. Now picture that gas cloud. It was barely rotating, almost nothing. But it's collapsing, getting smaller, denser, more compact by the hour, by the year, by the million years. And as it collapses, that barely there rotation gets amplified, and amplified, and amplified again. What started as a gentle drift becomes a perceptible turn. What was a gentle turn becomes a definite spin. What was a spin becomes a roar. By the time the cloud has collapsed to a fraction of its original size, it's not rotating gently anymore. It's a whirlpool, a furious sweeping disk of gas and dust, rotating at speeds that would be incomprehensible to stand next to. Let me ask you to sit with that for a moment. We started with almost nothing, a random wobble too small to see. And that wobble, because the universe refuses to destroy angular momentum, got preserved. It got amplified. It became the spinning disk from which our entire solar system was born. Richard Feynman used to press this point in his lectures. He'd say that nature has this deep, almost stubborn tendency toward conservation. Mass is conserved. Energy is conserved. Angular momentum is conserved. These aren't bookkeeping rules that physicists invented to stay organized. They are bedrock facts about reality. And among them, conservation of angular momentum is one of the most relentless. The universe does not throw away spin. Not even a little bit of it. Now here's the natural next question, and it's one I think is absolutely beautiful. Okay, so we get rotation, we get a spinning disk. But why a disk? Why do solar systems look like flat pancakes? Why does our Milky Way with its hundreds of billions of stars look like a flat spiral rather than a sphere? Shouldn't gravity, pulling equally from all directions, collapse things into a ball? That's exactly the intuition. And that intuition is exactly half right. Here's the hidden assumption. If the gas cloud didn't rotate at all, if you had a perfectly non-rotating cloud, gravity would pull it into a sphere. Uniform, compact, round. That's what happens when there's no preferred direction. But our cloud is rotating, and rotation creates a preferred direction, the axis of spin. And in the plane perpendicular to that axis, there's a force pushing outward, the same force that keeps water in a bucket when you swing it over your head. That outward force resists compression in the plane of rotation. So the cloud can collapse easily along the spin axis, think of it as up and down, but it resists collapsing sideways. Picture a ball of pizza dough. Toss it in the air, give it a spin, and watch what happens. It flattens. The rotation spreads it outward while gravity pulls the top and bottom together. Keep spinning and eventually you have a flat disk. That's exactly what a gas cloud does. At the center of that disk, things get extreme. Gas piles up. More gas rains in from the outer regions. The temperature climbs. The pressure builds. And eventually, after millions of years of accumulation, the temperature at the core crosses a threshold. Hydrogen atoms, moving so fast they can no longer avoid each other, start smashing together and fusing. In a flash of nuclear fire, a star is born. Our sun was born exactly this way, about 4.5 billion years ago. A cloud of gas in the Milky Way began to collapse, formed a rotating disk, and at the center, the sun ignited. The disk around it, the leftover material still orbiting, still spinning that disk, became our solar system. Now here's where the story gets personal. When that disk formed, it wasn't empty. Billions of miles of gas and dust were swirling around the newborn sun. And in that swirling material, something remarkable started happening. Dust grains collided and stuck together. Small clumps attracted slightly larger clumps. Larger clumps swept up smaller ones as they traced their orbits. Over millions of years, through endless collisions and accretion, those particles grew from grains to pebbles, pebbles to boulders, boulders to mountains, mountains to planetesimals, and planetesimals to planets. And the critical point, the thing I want you to really notice, is that those dust grains were already moving. They were already orbiting the sun. They didn't start from rest and get pushed into motion. They were in motion the whole time, from the moment the disk formed. The angular momentum that made the disk spin was already present in every particle. When those particles merged into planets, they brought their angular momentum with them. That is why all 8 planets orbit the Sun in the same direction. That is why they all orbit in nearly the same plane. They didn't vote on it. They were born from the same spinning disk, and that disk's rotation is now their rotation. Forever. Now, let's go one layer deeper, because something has been nagging at you this whole time, hasn't it? Maybe you didn't quite put it into words, but here it is. If gravity is constantly pulling the Earth toward the Sun, why hasn't the Earth fallen in? Gravity doesn't take a day off. It doesn't get tired. It has been pulling the Earth toward the Sun every second for 4.5 billion years. So why are we still here? Why haven't we spiraled inward and burned? The answer is one of the most elegant ideas in all of physics, and it is not what most people think. The Earth is falling toward the Sun. Right now, this second, as you watch this, the Earth is in free fall toward the Sun, but at the same time it's also moving sideways at a speed of roughly 67,000 miles per hour. And those two motions together create something remarkable. Think about throwing a baseball. If you toss it gently, it arcs and hits the ground a few feet away. If you throw it harder, it travels farther before it drops. Now imagine you could throw it fast enough. I mean, really fast, impossibly fast. At some point, the baseball is moving so quickly that the ground is curving away beneath it at exactly the same rate that gravity is pulling it down. The ball keeps falling, but the ground keeps falling away. It never lands. It just keeps going. That's what an orbit is. An orbit is not an escape from gravity. It's the perfect combination of falling and sideways motion such that you always miss the ground. You are perpetually falling and perpetually failing to land. The Earth misses the Sun 67,000 miles every hour, has been missing it for 4.5 billion years. And because space is essentially empty, no air resistance, no friction, no drag, nothing is slowing that sideways motion down. So the Earth will keep missing the Sun indefinitely, until something from the outside changes the equation. Feynman would have put it bluntly. An orbit is just a very elegant way of falling and missing at the same time. Isn't that a strange thought to sit with? Not a stable, secure circle in the sky, just a perpetual near miss. Every day, the Earth is failing to hit the Sun, and that failure is what keeps us alive. Now here's where the story scales up in a way that genuinely surprised me when I first understood it. A few minutes ago, we talked about gas clouds collapsing into spinning disks, and spinning disks becoming solar systems. That's the microscopic version of this story. Well, microscopic compared to what I'm about to describe. Now scale up, way up. We're talking about the scale of galaxies. The Milky Way is a spinning disk about 100,000 light years across. It contains somewhere between 200 billion and 400 billion stars. And all of them are orbiting the galactic center in roughly the same direction, in roughly the same plane. Because the Milky Way itself formed from a collapsing cloud of gas, a cloud that had its own tiny wobble, its own residual angular momentum that got amplified as the cloud collapsed into the structure we live in today. The same story, different scale. And what created that initial wobble in the proto-galactic cloud? We need to push the clock back further, much further. 13.8 billion years ago, the universe began. Everything we can observe, every particle, every field, every force emerged from a state so dense and hot that our physics barely has language for it. And as the universe expanded and cooled, something crucial happened. The expansion was not perfectly uniform. Some regions were infinitesimally denser than others. Some pockets of space had just a little more matter, a little more energy. The differences were absurdly small. Physicists describe them as fluctuations at the quantum level, imprinted on the fabric of space itself in the first fraction of a second. But those tiny fluctuations, those almost imperceptible wrinkles in the newborn universe, they were the seeds of everything. Every galaxy, every star, every planet. As the universe expanded and cooled, those slightly denser regions began to gravitationally attract more matter. Clouds formed. Clouds collapsed. The wobbles in those clouds were preserved and amplified. Rotation emerged. Disks formed. Stars ignited. Planets accreted. The spin of the disk that became our solar system is ultimately a distant echo of quantum fluctuations in the first heartbeat of the universe. That's not poetry. That's the physics. Everything you see spinning from the water going down your kitchen drain to the hurricane visible from orbit to the Andromeda Galaxy, 2.5 million light-years away, all of it traces back to those initial wrinkles, to that first tiny asymmetry, to the fact that the Big Bang was not quite perfectly uniform. Let that land for a second. The coffee you're going to swirl in your mug tomorrow morning. The storm that will hit the Gulf Coast next September. The galaxy your great-great-grandchildren will look up at through a telescope in 1,000 years. All of it connected. All of it flowing from that first imperfect, beautiful, asymmetric bang. All right. Now let's bring this home. Let's talk about something you've seen on the news, probably multiple times this summer. Hurricanes. Why does a hurricane spin? Why does every major storm system on Earth rotate? And why does it rotate in a different direction in the southern hemisphere than in the northern hemisphere? Here's the hidden assumption most people carry around, that the air just kind of swirls naturally. That wind plus low pressure equals a spiral, the same way water spirals down a drain. But that's not quite right. Or rather, it's right for the wrong reason. And the reason it's actually right is much more interesting. When a patch of ocean heats up, say, the warm waters of the Gulf of Mexico in late summer, the air above it gets warm too. Warm air is less dense. It rises. And when air rises, it leaves behind a region of lower pressure. The air around it rushes in to fill the gap. But here's the thing. That rushing air doesn't travel in a straight line. It can't, because the Earth is rotating. Think about it this way. Imagine you're standing at the equator. The Earth's surface at the equator is moving eastward at about 1,000 miles per hour just from the planet spinning. Now move to, say, Montana. At that latitude, you're still spinning eastward, but the circle you're tracing is smaller, so you're moving at maybe 500 or 600 miles per hour eastward. When a parcel of air near the equator moves north, it carries that 1,000 miles per hour eastward velocity with it, but the ground underneath it is now only moving at 600 miles per hour. So, relative to the ground, the air appears to curve to the right. The ground isn't keeping up. This is called the Coriolis effect. And it is the reason every major storm in the northern hemisphere rotates counterclockwise. The air rushing into the low-pressure center gets deflected to the right, and the whole system ends up turning counterclockwise. In the southern hemisphere, the deflection goes the other way, so storms spin clockwise. Now watch what happens once that rotation starts. Air rushes in toward the center, toward the low pressure. As it spirals inward, it moves toward a narrower circle. And what do we know about things moving toward a narrower circle while they spin? The figure skater, arms coming in, rotation accelerating, angular momentum is conserved. As air converges toward the storm's center, the rotation tightens and speeds up. The storm feeds on the warm ocean below, drawing up energy and moisture, and that energy drives the inflow, which tightens the spin, which draws in more air. It's a feedback loop. A hurricane is angular momentum conservation in action, driven by thermal energy from the ocean and shaped by the rotation of the Earth itself. The same law, operating at a human scale this time. The same law that built our solar system is building that hurricane offshore. Tornadoes are even more dramatic. When a thunderstorm's updraft is strong enough, it can interact with wind shear winds at different altitudes blowing in different directions, and that interaction begins to rotate a column of air. The rotation starts broad, but as the updraft pulls that rotating column upward and inward, the column narrows, and as it narrows, it speeds up. A column of air that was rotating lazily over dozens of miles can be compressed into a funnel hundreds of feet wide, spinning at 200 miles per hour or more. Angular momentum conservation, same law, smaller scale. So now let's put three things side by side. The accretion disk that became our solar system. The hurricane forming over the Gulf of Mexico, the tornado developing over the Kansas plains. Three completely different sizes, three completely different contexts, one law. That's what Feynman meant when he said, the most exciting thing about physics isn't any particular discovery, it's the moments when you realize that things that looked completely different are actually the same thing, described by the same equation. The universe in this sense is not a collection of unrelated phenomena, it is one story told at different scales. Now, naturally a question starts to form, and it's a good one. If angular momentum is conserved, if spin is preserved through every transformation, what happens when a star dies? Stars don't live forever. Our sun has burned for about 4.5 billion years, and it has roughly 5 billion years left. But even the sun will eventually run out of hydrogen fuel, and when it does, things will get interesting, to put it mildly. But let's talk about the stars that are more dramatic than the sun, the ones that don't go quietly. For stars significantly more massive than the sun, the end comes suddenly. The core of the star has been fusing heavier and heavier elements: helium, carbon, oxygen, neon, silicon, each stage of fusion producing less energy than the last. Then one day the star tries to fuse iron, and iron won't play along. Fusing iron consumes energy rather than releasing it. So in a fraction of a second, literally less time than it takes you to blink, the core support disappears. The outer layers of the star, which had been held up by the outward pressure of nuclear fusion, suddenly find themselves with nothing to push against. They fall inward. And when I say fall inward, I don't mean gradually. I mean in about a quarter of a second, the core of the star, a core that might be as massive as the sun, collapses from several thousand miles across to about the size of a city, New York City. That's it. Everything that was slowly rotating in a massive star is suddenly compressed into an object 10 miles across. Remember the figure skater. A neutron star can spin hundreds of times per second. Some of them spin more than 700 times per second. Let that register. 700 full rotations per second. In the time it takes you to snap your fingers, a neutron star completes more rotations than you could count. Why? Because it was the core of a star that was rotating slowly, by cosmic standards. And then that core collapsed by a factor of tens of thousands. The angular momentum was conserved. The radius got smaller. The speed exploded. These objects pulse with military precision, sending out beams of radio waves that sweep past us like lighthouse beacons. Astronomers called them pulsars, and when they were first detected in the 1960s, the signals were so regular, so mechanical, that the astronomers who found them briefly thought they might be signals from an alien civilization. They nicknamed the first discovered signal LGM-1, Little Green Men. That's how startling the precision was. But it's not alien intelligence. It's angular momentum conservation, taken to the extreme. Now, what about stars? Even more massive. What about the ones that collapse beyond even the neutron star stage? For the most massive stars perhaps 20 or 30 times the mass of the Sun, the collapse doesn't stop at a neutron star. The gravity is so overwhelming that even the quantum pressure that holds neutron stars together gets crushed. The matter keeps collapsing, past any structure we know of, into what we call a black hole, a singularity, a region where our current physics admits it doesn't know what's happening. But here's what's remarkable. We know the black hole spins. We can measure it. Some black holes rotate at close to the speed of light at their outer boundary, what physicists call the ergosphere. The spin is encoded in the geometry of space-time itself around the black hole. Think about that for a moment. A black hole is the most extreme object in the known universe. It's a place where time slows, where light can't escape, where our equations break down. Nearly every law of physics we know gets complicated near a black hole. But angular momentum? Angular momentum goes right on being conserved. The spin of the star that died to form that black hole is preserved in the black hole's rotation. Billions of years later, that rotation persists. The spin that began as a tiny wobble in a gas cloud outlasts the very star that amplified it. It outlasts the supernova that killed that star. It persists inside the most extreme object the universe can produce. That's not just a fact about physics. That's a statement about the depth of this law. Conservation of angular momentum doesn't have an off switch. All right, now let's shift gears slightly. Let's talk about something beautiful. Let's talk about Saturn. You've seen pictures of Saturn's rings. They're iconic, that gorgeous flat disk of material surrounding the planet, gleaming in reflected sunlight. But what are they, exactly? And how did they form? Saturn is the second largest planet in the solar system, which means its gravitational pull is enormous. Material is constantly being attracted toward it: moons, comets, stray asteroids. But here's the thing about getting close to Saturn. If you get too close, you don't make it to the surface. You get torn apart. The reason is something called the Roche limit, named after the 19th century French astronomer Edouard Roche. When an object gets close enough to a massive body, the gravitational pull on its near side becomes significantly stronger than the pull on its far side. The difference in pull, the tidal force, begins to exceed the object's own self-gravity, the thing that was holding it together. At that point, the object simply falls apart, shredded by tidal forces before it can ever coalesce into a moon. So, within Saturn's Roche limit, material can't clump together to form moons. It stays as fragments, billions of chunks of rock and ice, ranging from the size of a grain of sand to the size of a house, all orbiting Saturn in the same direction, in the same plane, like a miniature accretion disk. That's Saturn's rings. a disk of material that never got to become a moon. And if you look closely at the rings in photographs, in data from spacecraft like Cassini, you see that they're not uniform. There are gaps. The most famous is the Cassini division, a dark band thousands of miles wide that separates the main ring regions. That gap exists because of orbital resonance. There are moons orbiting Saturn outside the rings, Mimas for instance, and their gravity influences the orbits of ring particles that happen to have the right period. Over millions of years, those repeated gravitational nudges clear out the particles in those orbital slots. The gaps are carved by the same gravitational dance that sculpts the solar system itself. The rings of Saturn are not a decoration. They're a case study in orbital mechanics, in angular momentum conservation, in the way gravity and rotation interact to produce structure from chaos, which brings us to something even grander: the spiral arms of the Milky Way. When you see images of our galaxy or of similar spiral galaxies like Andromeda, you see those sweeping, graceful arms curling outward from the center. They look like permanent structures. Like the galaxy was shaped that way and has always been that way. But they're not permanent in the way you think. The spiral arms of a galaxy are not physical groups of stars that orbit together. They're more like a traffic jam. Here's the analogy. You're on the highway at rush hour. There's a slowdown ahead, maybe construction, maybe an accident. The cars in the slowdown are moving slowly. Cars from behind are catching up to them. So the dense region of cars, the traffic jam, persists, even as individual cars move through it and out the other side. The jam itself isn't made of the same cars from moment to moment. It's a pattern, a wave of density that moves through the stream of traffic. The spiral arms of a galaxy work the same way. They're density waves, regions where stars and gas slow down slightly as they orbit the galactic center, causing a pile-up. Stars from the inner part of the galaxy, moving faster, catch up to the arm, slow, pass through, and continue on. Stars from the outer part, moving slower, fall behind the arm and eventually get overtaken by it again. The arm is a pattern in the flow, not a fixed structure. But here's why this matters for our story. As gas clouds drift into the spiral arm, they get compressed. Remember what happens when a gas cloud gets compressed? The pressure builds, the angular momentum gets focused, and the collapse begins. Stars are born preferentially in the spiral arms, triggered by the density wave passing through. The spiral arms of our galaxy are star factories. And the machines in those factories run on the same principle we've been talking about all along: conservation of angular momentum, taking a wobble and turning it into a world. Now I want to do something a little different. I want to ask a question that sounds almost absurd at first, but stay with me, because it leads somewhere profound. What if there were no rotation? Not less rotation, not slower rotation, none. Imagine a universe where that first primordial wobble never happened, where every gas cloud that ever formed was perfectly, mathematically, impossibly still. What does that universe look like? Here's what the physics tells us. A non-rotating gas cloud, collapsing under gravity, doesn't form a disk. It falls straight in. Every particle from every direction plunges directly toward the center. There's no sideways motion to create orbital paths. There's no angular momentum to form an accretion disk. The whole cloud just piles up in a single dense lump at the center. Stars might still form. The conditions at the center might still be hot and dense enough for nuclear fusion. But without a disk, there's no structure for planets to form in. Without planets, there are no solid surfaces. Without solid surfaces, there's no place for water to pool, no place for chemistry to accumulate and comexify, no place for life. The universe without rotation is a universe of stars and nothing else. Billions of solitary suns, burning in an empty void with no planets orbiting them, with no oceans, no atmospheres, no mountains, no morning light coming through a window. Your morning cup of coffee requires rotation to exist. Your body requires rotation to exist. This conversation requires rotation to exist. Think about what that actually means. Rotation is not just a feature of the universe. It is a prerequisite for the universe to be interesting. Now here's where the story turns the most personal it's going to get. And I want you to really stay with this one. Your body is made of atoms. Carbon, oxygen, nitrogen, iron, calcium. These elements didn't exist right after the Big Bang. In the first few minutes of the universe, the only elements that formed were hydrogen, helium, and a tiny bit of lithium. That's it. The periodic table was nearly empty. Where did carbon come from? Where did the oxygen in your lungs come from? The iron in your blood? It came from stars. Specifically, it came from stars that lived and died before the sun was born. Inside a star's core, nuclear fusion doesn't just produce energy, it produces new elements. Hydrogen fuses into helium, helium fuses into carbon, carbon into oxygen, oxygen into neon, and so on, up the periodic table, all the way to iron. When a massive star explodes in a supernova, it doesn't just die, it detonates, scattering all those elements it spent millions of years building into the surrounding space. Those scattered elements became part of new gas clouds. Those clouds collapsed with their angular momentum, their residual wobble, their seeds of rotation. They formed new disks, new stars ignited at the centers of those disks. And in the outer regions of those disks, those elements, the carbon and oxygen and iron that the previous generation of stars had manufactured, accreted into rocky planets. One of those planets is the one you're standing on. And the atoms in your body, the carbon in your DNA, the oxygen you breathe, the iron that carries oxygen through your blood, those atoms were forged inside a star that exploded before the sun existed. You are, in the most literal possible sense, made of stardust. And the stardust that became you got here because of a spinning disk, because the cloud that formed our solar system had a wobble, because that wobble was conserved, because angular momentum does not yield. You are the universe's angular momentum, expressed in a form that can look up at the sky and wonder where it came from. Let me say that again, because I think it deserves it. The spinning of our galaxy and the spinning of the cloud that became our solar system, and the spinning that formed the disk, and the disk that formed the planets, and the planet that gave rise to life, and the life that eventually became you, it is one continuous chain, connected all the way back to the first moment of asymmetry in the Big Bang. The universe began. It was not quite perfectly smooth, and that imperfection echoed forward 14 billion years to produce this moment. You, watching this, wondering about the universe, are that echo. I think Feynman would have found that deeply moving. He had this quality that's rare even among great scientists, the ability to look at a physical law and feel something, not just intellectual respect, but genuine wonder. He once said that a scientist's job is to maintain the childlike capacity to be astonished. And the more deeply you understand physics, the more astonishing it becomes. Not less, more, because the surface story about rotation is already interesting. Spin a top, watch it gyrate. Spin a galaxy, watch the arms form. That's the surface. But the deeper story, the one we've been tracing today, is that the same principle governs all of it. From the quantum wobbles in the infant universe, to the hurricane forming off the coast of Florida, to the neutron star spinning 700 times per second, it's one law, one principle. Total angular momentum is conserved, always, without exception. That kind of universal consistency, the same rule, operating at every scale, in every context, is not something you can take for granted. And Feynman didn't. He was explicit about the fact that the laws of physics didn't have to be this way. The universe could have been different. It could have been chaotic, inconsistent, scale-dependent. The fact that the same equation describes the motion of a dust grain and the orbit of a galaxy is not obvious. It's remarkable. And recognizing it as remarkable is, I think, part of what it means to really see the world. Now, and this is the part I was waiting to get to, let me be honest about something. We've answered why things spin. We've traced the mechanism from quantum fluctuation to cosmic structure. But there's a question underneath that one that physics, as it currently stands, doesn't fully answer. And Feynman was very clear that intellectual honesty requires acknowledging this. Why is angular momentum conserved at all? The deepest answer in modern physics comes from a theorem by Emmy Noether, one of the most important mathematicians of the 20th century. She proved that every conservation law corresponds to a symmetry in nature. The conservation of energy corresponds to the fact that the laws of physics don't change over time. They worked the same way 1 billion years ago as they do now. The conservation of angular momentum corresponds to the fact that the laws of physics don't depend on direction. There's no special orientation in space. Rotate your experiment, and the physics comes out the same. That's beautiful. That's genuinely beautiful. Conservation of angular momentum is a consequence of the fact that the universe has no preferred direction. Isotropy, physicists call it. Space is the same in all directions. And because of that, rotation is preserved. But then you might ask, well, why is space isotropic? Why does the universe not have a preferred direction? And at that point, we've reached the edge of what current physics can answer. We don't know. We can describe what's true. We can't always explain why it's true. Feynman was at peace with that. He thought it was actually a good thing, that not knowing something isn't a failure, it's a direction. Every unanswered question is a door. And the fact that we can get to the edge of knowledge and clearly see the door, that's progress. That's science doing what it's supposed to do. So we know that everything spins because of a tiny primordial wobble, preserved and amplified by angular momentum conservation. We know that conservation law arises from the isotropy of space. And we know that we don't yet know why space is isotropic. There's more to find. There always is. Before we close, I want to mention a few things that don't quite follow the main pattern because the universe is never quite as neat as we'd like, and those exceptions are where you find the most interesting questions. Uranus, for instance. Most planets spin on axes that are roughly perpendicular to their orbital plane, like a top spinning upright, but Uranus is tilted about 98 degrees. It's essentially rolling on its side as it orbits the Sun. The best explanation we have is that something enormous, a planet-sized object, collided with Uranus early in the solar system's history and knocked it sideways. The angular momentum was preserved, but the direction changed. Uranus is still spinning. It just does it lying down. Venus is stranger still. Venus rotates in the opposite direction from most planets, so if you were standing on Venus, you'd see the Sun rise in the west and set in the east. Why? We're not entirely sure. It might be an ancient collision, or it might be that Venus's thick atmosphere created tidal effects over billions of years that gradually reversed its spin. But Venus is still rotating, the spin wasn't destroyed, just reversed. And then there are the comets and asteroids that arrive in our solar system from outside it, entirely what astronomers call interstellar visitors. These objects formed around other stars, in other rotating disks. They carry their own angular momentum from those distant origins. When they pass through our solar system, they don't follow the same orbital plane as the planets. They come in at wild angles, orbiting in the wrong direction, swooping through from above or below the ecliptic. They're strangers here, but they're spinning too. Their rotation reflects their own birth, their own home cloud, their own fragment of the universe's angular momentum budget. Every spinning thing carries a history in its rotation. The direction it spins, the rate it spins, the axis it spins around, all of that is a record of what happened to it, of what clouds it came from, what collisions it survived, what forces shaped it over billions of years. Rotation is not just a behavior, it's a biography. Now let's come back to where we started. Why does everything spin? The answer, distilled to its essence, is this. In the first moments of the universe, the initial conditions were not perfectly uniform. Small, random asymmetries, quantum wobbles imprinted on the fabric of space ensured that nothing would ever be perfectly still. Those wobbles were preserved because angular momentum is conserved, and they were amplified every time gravity caused matter to collapse and compress. What was almost nothing became something enormous. What was a faint whisper became a roar. From that process, galaxies, solar systems, planets, the conditions for liquid water, the conditions for complex chemistry, the conditions for life, for consciousness, for curiosity, for you. Here's the thought I want to leave you with tonight. Go outside this evening if you can. Look up. What you're seeing isn't a static sky. Every star you can see is spinning. The planets you can't see are orbiting at tens of thousands of miles per hour. The galaxy you're embedded in is rotating, carrying the Sun and every other star in a vast, slow arc around the galactic center. A journey that takes our solar system about 225 million years to complete. We're mid-journey. Somewhere in the middle of a lap we started before the dinosaurs existed. And you are on a planet that is spinning at about 1,000 miles per hour at the equator. That planet is orbiting the Sun at 67,000 miles per hour. The Sun is orbiting the galaxy at roughly 500,000 miles per hour. You have never been still, not for a single second of your life. You are in constant, nested, layered motion that traces back, link by link, to the quantum irregularities of the Big Bang. That's not an uncomfortable thought, or at least it doesn't have to be. Because what it means is that you are not separate from the universe's story. You are not a spectator watching the cosmos from the outside. You are made of the same material that was forged in stellar cores and scattered by supernovae. You carry the same angular momentum in your atoms that has been threading through the universe since nearly the beginning of time. The universe spent 13.8 billion years spinning its way toward complexity. And part of what it produced as almost an afterthought almost accidentally, on a small rocky planet around a fairly ordinary star, was the ability to look back at itself and ask, why? You are that ability. The universe asking itself why it spins. And now you know. That seems like a pretty good reason to be grateful for a spinning universe. Thank you for spending this time on Feynman's Path. If something we explored today changed the way you see the night sky, or the next hurricane on the news, or even the way water goes down your drain, then we did what we set out to do. I'll see you in the next one.